Good morning, everybody. Hopefully you can all see my screen. So like Anami mentioned, I'm going to be talking about the software that sends rockets to space. So this talk is mainly focused on the software development during the Apollo era. So the software development during the Apollo era was mainly hardware focused. So essentially that just means that the hardware was tightly coupled to the software. So it was very much like fixed function hardware. As for the programming languages that were used, it was mostly assembly. There was a little bit of Fortran in there, and then they also developed their own high order assembly language so that they didn't have to write so much just essentially basic assembly code. As for the challenges involved with writing software for the Saturn V rocket, there was a lot of manual coding that was involved with that. So that was a very labor-intensive process. The programs had to manually write the code for each specific task and subsystem, and debugging was often a challenging and very time-consuming process. And what I mean by manual coding is that there was no higher language like C or C++ or something like that, obviously for the time period. And then also another challenge that they faced was limited computing power because they had a lot of weight restrictions, obviously, for what they could send up into space. So that definitely limited the amount of power that they could actually have with the software and hardware that they were sending up. So yeah. As for the design flow that they used a similar approach to sort of what we do now with modern software development. So they had requirement analysis, they had software architecture and design, and they had obviously the actual writing of the code, which was the assembly language programming process that they went through. And then obviously after they've written the code, they have to now integrate that with the hardware. And that was the software integration part of that. And then for testing, they had verification and validation. And finally, they had to document and actually maintain the hardware. So you heard me use the term ACG before. So what does that actually stand for? That is actually the Apollo Guidance Computer, which was the main computation unit aboard the Apollo rocket. It was responsible for guiding and controlling the spacecraft during the various mission phases. So on the left, there's an image of what it actually looks like inside of the computer. And you can see that there's little modules, and that's actually where all the individual processes and programs are actually written onto those. And on the right is a more complete version, and there's a little like sort of interface that they had to use, and you can see that there's only numbers pretty much on it. So it wasn't very interactive. As for the memory that they use, so obviously we've got the brains of it. So where was all this computer software actually stored? So it was stored on something called core rope memory. It's also known as woven core memory or magnetic core rope memory. And it's a type of read-only memory. And it was primarily used during the early computer system design phases in that era. So essentially, wiring of the core rope was a very tedious process that took up to 8 weeks and cost about $15,000 per module. As a result, the computers code needed to actually be frozen months in advance because they actually are like weaving this memory by hand, as you can see by the image on the left. So like if you had a bug or something like that, well, you're pretty much out of luck. And then on the very far right, you can actually see what it really looks like very close up. So it's like these magnetic rings, and essentially they're magnetized. So if it's spinning the one way, then it's a 0, and if it's spinning in the opposite direction, it's considered a 1. So that's essentially how the binary worked on this sort of memory. So why did they use core rope memory? So core rope memory was actually used for its reliability and its radiation resistance. So core rope memory was mainly known during that time for those two things. And obviously when you're in space and there's a lot of radiation, you want your hardware to be very radiation resistant and reliable on you, especially when there's a lot of human lives on the line. So core rope memory is also a type of non-volatile read-only memory. So essentially, that means that you can't really like modify or erase the data, which is also very important for these types of missions. So why was radiation resistant actually very important during this era? So there was this thing, well, there is this thing called bit flipping. So also known as single event upset is a phenomenon that can occur in electronic systems, including those used in space missions. Bit flipping refers to spontaneous changes of a binary bit from a 0 to a 1 or from a 1 to a 0. And it's generally caused by the impact of high energy particles such as cosmic rays or electronic components. In a space environment, prevalence of high energy particles is obviously very high because there's no atmosphere to actually shield the hardware from these things. So these particles penetrate the electronic systems, including memory cells, and can occasionally cause bit flipping, leading to potential errors in the data. So there's actually two very famous incidents of bit flipping on Earth. One was a Mario 64 speed run that caused the fastest speed run in the world. And to my knowledge, no one's ever been able to break it. And then the other was caused in Belgium during one of their voting days. And it was actually the first implementation, I believe, of electronic voting. And one of the candidates got like 4,000 extra votes, and there actually wasn't even 4,000 voters. So that's how they were actually able to detect that one. So obviously now that you know what bit flipping is and what it does, how do you actually combat this? So one of the things that they did was they had redundancy. So they basically had two of everything inside of the rocket. And then they also had what was called the voting system. So essentially these two computers are running in parallel. So they have two ACG computers and they're running in parallel, and they basically evaluate each other's work, and whichever one is the most correct, that's what they actually go with. And then they also had things like error correction codes that they could use, or if you prefer, error correction algorithms. And then obviously they implemented like lots of radiation resistant components and shielding, and they grounded the components to make sure this didn't happen. Just some interesting facts before I let you guys go. The ACG computer, aka the Apollo Guidance computer, was one of the first computers to use integrated circuits. The entire computational module on the rocket actually weighed about 2 metric tons and was situated at the top of the rocket. And the total memory of the entire rocket, that's all the components combined, was about 2.5 megabytes of RAM. And then the memory capacity of the actual ACG computer itself was actually only about 36,864 words, which amounted to about 72 kilobytes of actual memory that the computer actually had to work with, which compared to today's standards is not a lot at all. And then the actual performance of the computer, which I find quite interesting, is that it could perform roughly about 2 million operations per second, which if you compare that to a 4-core CPU, relatively low end today, which can produce about 200 billion operations per second. So you can see we've come a long way since then.